Good morning, everyone. My name is Houda Kacimi, a PhD student at the Faculty of Sciences at Ibn Tufayl University in Kenitra. I would like to sincerely thank you for accepting my article for publication. In my presentation today, I will take you through the main sections of my article titled Comparison of Multilayer Perceptron and Nonlinear Autoregressive Models for Wind Speed Prediction. To ensure a clear understanding, the presentation is organized into five key parts. First, I will provide an introduction to the topic, including the motivation behind the study and the research objectives. Next, I will discuss the theoretical background of artificial neural networks, focusing on the two models used in this study. Following that, I will describe the methodology employed, including the data preparation and the experimental setup. Then I will present the result obtained from the experiments and discuss the performance of the two models in terms of consistency. Finally, I will summarize the main contribution of the study. Let us now begin with the introduction. Wind is the primary driving force behind wind energy, which is the renewable energy source characterized by its variability and unpredictability. The random nature of wind patterns stems from complex atmospheric dynamics influenced by geographic location, time of day, and seasonal changes. This inherent intermittency poses significant challenges for managing wind power generation, as fluctuations in wind speed can lead to irregularities in energy production. Effective integration of wind energy into the power grid requires sophisticated forecasting techniques and energy storage solutions to mitigate the effect of these inconsistencies and ensure a stable energy supply. The purpose of this study is to compare two artificial neural network models, namely the multilayer perceptron and nonlinear autoregressive with the exogenous inputs for predicting wind speed in Dakhla City. Addressing the challenges of wind speed variability requires advanced of advanced predictive tools capable of capturing the complex and dynamic nature of atmospheric patterns. This brings us to artificial neural network. Let us now explore the genesis and the principle of these networks. The genesis of the artificial neural network, an information processing model, drew its inspiration from the intricate working of the human brain. Learning algorithms based on statistical methods are used to improve these networks. They are located on the one hand in the category of statistical applications, which allows them to create extensive, flexible, and partially structured functional spaces. And on the other hand, in the sphere of artificial intelligence techniques, promoting decision making which rely more on perception than on formal logical reasoning. A neural network is typically composed of several key components. It's characterized by inputs that come from previous neurons, with each input associated with a weight, representing the connection strength. These weight values are calculated during the learning phase in the hidden layer, which consists of several neurons and an activation function. As previously noted, we use two types of neural networks. The MLP is a standard neural network that consists of input, hidden, and output layers. It uses the error backpropagation algorithm, which is essentially based on gradient descent. This backpropagation algorithm calculates the difference between the desired output and the output produced by the network. To mitigate this mistake, information is passed from the output to the input by modifying the weights. In contrast, the NARX model, it's a variation of recurrent neural network, employs training methods akin to those found in traditional networks using the gradient backpropagation algorithm. NARX distinguishes itself by its capacity to effectively analyze nonlinear time series, particularly dynamic systems. Additionally, its gradient descent algorithm demonstrates swift convergence in comparison to alternative networks. Various other forms of deep recurrent neural networks exist as well, and this is an illustration of the NARX structure featuring both a closed loop and an open loop. We can be observed in figure 3A and B. The unique capabilities of the NRARX network, such as its efficiency and analyzing nonlinear time series and dynamic systems, make it a perfect candidate for wind speed prediction. With, with this in mind, let us now explore the methodology employed in the study. The goal of this study is to discover which predictive network, MLP or NARX, is the best effective at forecasting wind speed in Dakhla. Dakhla is located in southern Morocco. The city is notable for its continuously windy climate, with the winds gust up to 30 kilometers per hour year round. Weather data for Dakhla was collected hourly for 3 years, from 2018 to 2020. The table 1 shows the hourly data in local time, which includes the wind speed, temperature, atmospheric pressure, dew point temperature, and humidity. The table also emphasizes the advantages of pre-processing in improving the conception and the extraction of meteorological data. We process the meteorological data in Excel before doing MLP modeling with NN tool and the NARX modeling with the NN start in MATLAB. Pre-processing weather data makes it easier to select parameters for predictive models. Having established the methodology used in the study, including the preparation of data and the implementation of the MLP and NARX models, we now move on to the results. In this section, I will present the performance metrics and compare the results of both models. First, the correction coefficient between variables. To optimize the input variables for our neural network and avoid the computational cost of using all of the variables listed below, we calculated their correlation coefficient. The table 2 shows the strong relationship between temperature and dew point temperature, with the highest correlation coefficient of 0.4997. This implies that the dew point temperature is comparable to the temperature and will have no significant impact on training. As a result, we decide to abolish the dew point temperature variable. After several attempts, we varied the number of inputs, starting with the three: wind speed, pressure, and temperature, and then added a fourth: humidity. We also experimented with the different numbers of neurons in the hidden layer, ranging from 5 to 25, to determine the ideal configuration for accurate wind speed prediction. Our research revealed that the network with 4 inputs and 25 neurons in the hidden layer was the most effective. This design regularly outperformed the other configurations in terms of prediction, correctness, and processing efficiency. The figure 4 depicts the processes for training the MLP network. First, data is used to fit the model, which suggests the model must observe, process, and learn the data. Second, validation is performed to evaluate the model fit while defining the parameters. The goal is to optimize the parameters to produce a strong model. Finally, the testing process performs the final examination of the model to make it more organized. However, as illustrated in Figure 4, the R values for the training, validation, and test phases are all comparatively low. This indicates the model's inability to generate correct predictions and produce appropriate results. In general, we determined that the LM backpropagations approach produced regular results with an R value of 0.51539. After training the multilayer perceptron using Levenberg-Marquardt backpropagation, we conclude that the model was not able to properly train and clearly predict the proposed inputs. The following figure 5 shows the mismatch between the real series and the predicted series. We conclude that the multilayer perceptron is too classical a model and is still not able to solve high complexity problems. It essentially illustrated the significant contrast between the model predicted wind speed and the observed wind speed. The difference between these two data sets is incontestably clear. For NARX open loop, the figure 6 shows the results of the NARX model, which was optimized with the scaled conjugate gradient algorithm. The training and validation phases have the same coefficient of determination of 0.9998, and testing phase have 0.995 as a coefficient of determination. This high R values suggest a practically perfect fit of the model to the data at all stages, demonstrating the model's strength and exactness. When comparing the NARX model's performance to that of the LM model, it's clear that the NARX model's predictions are quite similar to the actual wind speed data. This is verified by a high correlation coefficient between expected and actual wind speed, demonstrating a strong linear relationship with low forecast error. The figure 8 shows the results of the NARX model, which was processed using scale conjugate gradients. Examining the LM model, the NARX data closely align with the actual wind speed data, showing a correlation coefficient. The figure 8 shows a visualization of both anticipated and real wind speeds, demonstrating the NARX models unresolved performance in wind speed prediction. In table 3, we used the root mean square error, a metric widely used in climatology, forecasting, and regression research. The choice was made to validate the data and demonstrate that in our investigation, the NARX model outperformed the MLP model. Lower RMSE values indicate more correctness. Our result demonstrate that the nonlinear autoregressive with exogenous inputs model had a considerably lower the root mean square error than the MLP model, indicating a better capacity to estimate wind speed in Dakhla City. And for conclusion, wind speed predictions in Dakhla City were conducted employing two artificial neural networks, MLP and RNN. Both networks shared a similar architecture with four input variables. Additionally, each network included a hidden layer compressing 25 neurons and an activation function with the wind speed at time t serving as the decisive factor in the outlier. The NARX model training using scale conjugate gradient showed strong performance, soft in R value, while the Levenberg-Marquardt backpropagation method performed less satisfactorily with an R value. This comparison highlights the superior ability of the NIRX model over MLP in effectively addressing nonlinear and complex situations. For future research, it would be valuable to explore alternative neural network models such as long short term memory networks or gated recurrent units to evaluate if they can further enhance prediction correctness in similar nonlinear conditions. And thank you for attention.